Okay, so in the last video, we finished chapter one, which was our review on pre-calculus. So and in this lecture, we're going to start in chapter two, and this is where we begin to think about calculus. This is when we're going to introduce basically the fundamental ideas of calculus. So this is chapter two. It's on limits and derivatives, and we're going to be in 2.1, which is a tangent and velocity problem. So I encourage you to read 2.1. I'm going to kind of diverge from what the way the book presents these things, but it's still helpful to read through that section. I'm not going to really talk about the tangent problem. The tangent problem is going to come up, but it's not going to be like the focus. I'm not going to try to motivate calculus or like why we care about calculus by looking at the tangent problem. To me, that's just more of an abstract mathematical problem. I care more about the velocity problem because that is really the motivation historically, or well, I don't want to say historically because not I'm by no means a historian mathematician mathematics, so I don't know the full history. I'm not going to pretend to know the full history. But I think definitely the velocity problem was one of the problems which motivated the introduction of calculus. And I think it's more of like a concrete problem, and problem that you definitely want to be concerned about, especially if you care about physics or science. You want to be able to talk about velocity or which is also can be called a instantaneous uh, instantaneous rate of change of your position. So let me share my screen. And you can see what I'm seeing. So one of the best ways to learn and understand a new subject, particularly subjects and theories in mathematics, is to understand where or why the subject or theory arose. What was the motivation for introducing the subject or theory? What were the problems that the pioneers of the subject or theory were trying to solve? And understanding the motivating problems, knowing a bit of the history, maybe not the full history of the development of the subject or theory, can be really helpful in understanding the subject or theory itself. Otherwise, the theory can just look like a bunch of useless abstract nonsense. And as with most theories and concepts in mathematics, calculus has its roots in very concrete problems in physics, which mathematicians were trying to solve. So, under trying to mathematically solve problems in physics is a great source of development for mathematics. Like physics and mathematics kind of like they're parallel. They and but well, not parallel, but they kind of are developed simultaneously. They kind of piggybacked off each other. So there was physics solving problems in physics definitely motivated the introduction and development of theories in mathematics and vice versa. So now, if you enjoy the technology advances of modern science, which you surely do, seeing as we're using our laptops right now to watch this lecture and learn about calculus, then you will definitely care about physics. And if you care about physics, then you got to care about mathematics, or at least calculus in this case. So calculus is a really amazing branch of mathematics that has so many applications, and it's hard to overstate the importance of it, and has led, and then mathematicians have tried to generalize the idea of um, calculus, and that has led to the development of very powerful mathematical theories, which in turn have more applications. So one of them I mentioned was topology, which, as I said, is kind of rubber sheet geometry, studying shapes in space under continuous transformations and deformations. So I talked about the torus and the coffee cup, the torus being, the donut shape. And that has lots of applications in physics, obviously, and biology and protein folding. Um, so there's definitely a reason to care about mathematics. But one of the problems that Isaac Newton and Gottfried Leibniz, the founders of calculus, along with some others, say like Rene Descartes, Pierre de Fermat, Blaise Pascal, the problem that they were trying to solve was that of instantaneous. One of them was instantaneous rate of change or motion. They wanted to be able to describe instantaneous rate of change or motion mathematically. So calculus emerged in response to trying to make this notion of instantaneous rate of change or mathematically rigorous. So one way of thinking about math calculus is that it's the mathematics of instantaneous rate of change. I mean, this doesn't fully and accurately describe calculus, but it gives us a good idea of what it's about. This actually only describes half of calculus, sometimes called differential calculus, and the other half is sometimes called integral calculus. But these are very closely, but this is very closely connected to differential calculus. So we're going to start in what's called differential calculus and then move to integral calculus. So regarding this problem of instantaneous rate of change, Newton and Leibniz had some really brilliant ideas. So let's consider the following thought experiment to try to recreate some of the fundamental ideas of calculus. So what we're going to think about is one-dimensional motion. So you can think about maybe a person walking along a line, maybe backwards and forwards, or maybe a car driving along a straight road backwards and forwards, or maybe just, well, even just more generally, a particle. Maybe thinking about like a particle moving. Maybe it's under the influence of gravitational force or electromagnetic force, and it moves along one-dimensional motion, or it moves in one dimension. And then, so let me pull up this animation. This is like the best I can find. It's kind of a cheesy animation, but they'll give you hopefully an idea of what's going on. So you can see this. So we have these two plots, time and position. We also have time and velocity, but I don't care about the velocity one. Just ignore that for the moment. But we have a car, actually two cars in this case, moving along one dimension. In this case, they're just moving forward, but you can imagine that they could back up. They could go forwards or backwards, and they both start out at this initial position right here, which you can call the origin. So this is the origin. So they're moving. You can imagine that they're moving along the real line, and they're moving in the positive direction. They're moving to the right of zero, and then of course you can move backwards. And so these are the plot of the position. So these plots are just so we have one-dimensional motion, but we have a two-dimensional plot. It's the position as a function of time. So we're going to think about the position, and it's going to be some function of time. That they're these particles or these cars or whatever you want to, however you want to think about them, they're moving in time. So we can describe their position as a function of time. And you can see at this point right here, you can see my mouse, it kind of tapers out and it becomes flat. And that just indicates the fact that the red car is no longer changing its position. It has at this particular time right here, it just does not change its position. All right, so here's how that unfolds. So just imagine something like that. So what we're going to say is we're going to imagine, we'll just say a particle moving uh, in say moving in one dimension, I guess. One dimension. We'll say along the real line. Uh, it's and so we can say its position. So if I give you a time, if I give you a particular time in the history of the universe, a particle, at least classically, is going to only occupy one position at a time, right? So there's this association, there's this mapping. I can give you a time and you can associate to a position of the particle. So, and it's a unique position. So this is going to be a function. So its position can be described, oops, oh, described by some function P, and we measure time with positive, non-negative, or non-negative numbers. So it's a function from 0 to infinity to r. So this is time, and this is gives you position. So the domain is the set of times at a given instance, and then the codomain r is position on real line. And then so given a time t, P of t denotes its position, oops, relative to 0. And that's like going to be our reference point. We're going to measure all positions and distances relative, or at least positions relative to 0, the origin. So we have like, I don't know, we have this real line, we have 0, and then maybe we have like a particle starts here, and then it kind of moves forward, and then maybe it stops here, and then it turns around, and then maybe it moves backwards. This is, of course, I'm drawing it off the line, but you can imagine it's like still on the line, moving backwards now, and then maybe it like ends up here. So it kind of goes forwards and backwards. So we can represent this with a graph. So maybe the graph looks something like, let's see, so you start at 0, you move in the positive direction, so maybe it kind of goes up like this, and then it goes down, and then it goes back through the origin at some point, and then it kind of goes like this, and maybe it does some other stuff. It doesn't really matter. So this will be time axis t, and this will be p of t, the position. And so it's kind of just moving around. And now we want to make sense of instantaneous speed, instantaneous rate of change. So this is the concept that we're trying to make sense of. How do we describe the velocity, velocity of the particle, and that i.e. the instantaneous, its instantaneous speed. What's its instantaneous speed? How do we do that? Crap, I can't spell right now. So how do we describe the velocity of the particle, i.e. its instantaneous speed? Well, we know how to describe average velocity. That's not that bad to do. So let's think about average velocity. So suppose we want to actually, let's say, so the question is, how do we describe the instantaneous velocity of the particle? Well, let's say we want to describe instantaneous velocity, like velocity at an instant. Like, so for example, if you're driving a car, the speedometer is basically giving you a very good approximation of your speed at any given instant. So we want to, how do we describe instantaneous velocity? Or that's kind of redundant. Instantaneous speed. Oh, no, wait. Well, yeah, the instantaneous velocity. Maybe I want to say not speed right here, but rate of change, instantaneous rate of change in its position. How do we describe instantaneous velocity? So let's see if this freaking thing is going to work. This, um, so I describe instantaneous speed or velocity at some time t0, say. So I just at some time t0. That's what we want to do. So let me copy this graph again. If I can. I want to bring it down here and whoops. Do that right. So copy this and then make it a little bit bigger though. I guess not, never mind. Anyways, so we have some time and maybe let's say, I don't know, let's say it's t0's here. So you occupy some position at that point in time. And you want to know what is the velocity at this time. So you definitely have some position. It's like kind of, I didn't draw the axis completely up to scale, but this would be like P of t, 0. Well, we know how to describe instantaneous velocity. Sorry, average velocity. So what is average velocity? Average velocity is pretty easy to describe. It's change in position divided by change in time. So where did you start? Where did you end? And where did you and how long did it take you to go from where you started to where you ended? So it's a pretty familiar idea. You get this average velocity, let's say over the interval like p a comma b, and that will be a subset of 0 to infinity. So we wanted to find the average velocity over that. So this quotient then really is just p of b minus p of a, because your position at time b and your position at time a divided by b minus a. Um, Actually, let's not use a and b. Let's say t. We got a lot of t's floating around, but let's say um, t1 and t2. So we have t1 and t2. So this will be t2, and then this will be t1. T2 minus t1. And let's just say like T1 is like right here. So T0 is going to be some time between T1 and T2. T2. And then you can look at the position here and the position here. So this will be like P of T1. And then up higher here will be P of T2. Now, so if I get this average velocity, this number right here, this is not my exact speed at any given moment, but it gives me a rough idea. So because t0 is between t1 and t2, that is, it's in this interval, this number right here, p of t2 minus p of t1 divided by t1 2 minus t1 is a rough estimate of my instantaneous damn it instantaneous velocity at t0, and we'll call velocity just call let's say it's a function from v from 0 to infinity to r. So this will be describe my velocity. So this quotient right here gives me a rough estimate, right? So maybe it might be a little bit this number right here might be a little bit smaller, maybe it's a little bit bigger than my actual instantaneous speed at t0, but it gives me a rough idea. So now, but here's the idea. This is the idea right here. What if we take um what if we take a smaller interval? So T1 and T2 are just any two numbers between which contain T0 between them. What if I can take a smaller interval T1, T2 about T0, and then I compute this fraction again? Well, I'm gonna be like, what I'm gonna be doing is like maybe I'll consider a number here and a number here, and it's between these two right here. And it's you're getting an average velocity on a smaller interval of time. So this should be better. So this should be a better approximation. Give a better approximation. And if you can just keep repeating this, you'll get a better, uh, let's say a better approximation of v of t, 0, our instantaneous velocity at this time. This is the function basically we want to describe. We want to be able to figure out how do we describe this instantaneous velocity? How do we make sense of this idea? And so that the idea is just keep repeating this process, like chop up the interval smaller and smaller and smaller and smaller, and you should get a better and better approximation. So in other words, what we want to do is when we want to take a quote unquote limit of intervals getting let's say containing t0 and getting smaller, like the interval is shrinking, it's getting almost to like a point. You take these intervals and you shrink it to a point. You keep compute every time you shrink the interval, compute the average velocity, shrink the interval, compute the average velocity, shrink the interval again, compute the average velocity. You're going to get a sequence um, of numbers. These and then the sequence is going to be your average velocities that should be giving you a better and better approximation of um, the instantaneous velocity. So we want to take a limit of intervals containing t0 and getting smaller. We want this smaller. So every time you shrink the interval, you're going to compute the average, whoops, velocity. You're getting a better and better approximation of velocity, and you'll get a sequence of velocities, let's say a sequence of average velocities, and they should approach the instantaneous velocity. So the instantaneous velocity is going to be some sort of limit, and we're going to make this even more precise later on. We'll give a very precise definition of what a limit is, what it means to take a limit of a function. So and your instantaneous velocity is going to be a sort of limit of average velocities. So let's try to just make this idea get precise again. Let's see, I can try to let me copy this. I don't know if it worked. Oh, here we go. I don't want two copies though. Oh, why this is not going away. No, I'm losing so much. All right, let's get rid of these graphs here. Try it again. So velocity, and then right here, let's do one copy. Okay, here we go. Except it didn't keep it highlighted. It's annoying. Okay, so let's try to move this over here. Okay, so let's set this up again. So we have, I think we had maybe t0 about here. And then this would be, okay, let's say this would be p of t. That's too small. Feel free to speed up the video, especially for times when my computer is lagging a lot. I don't know why it's lagging so much, not even that old. Um, Never had this much trouble in the past. Okay. So this is p of t0. And so the idea is we want to like to get a bunch of average, to get a sequence of averages which can approach or converge. And we'll define those terms more precisely later on. we want them to approach or converge the actual instantaneous velocity. So I want to consider points on the t-axis, which are close, getting closer and closer on either side. So the best way to do this is to let h be any number with the absolute value of h small. Then if you consider t0 plus h, then these are points in time. There'll be points in time close to t0. So h is just some parameter. And it's going to be such that the absolute value is a small number. So then if you take t0 plus h, this number is very close to t0 because h is roughly small. H could be positive or negative. So if h is positive, this will be a close point, close to t on the right of it. If h is negative, this will be a point close to t0 on the left of it. So maybe like if t is positive, maybe be like up here. This will be like t0 plus h if h is positive, and then maybe it'll be over here if h is negative. So t0 plus h. But you have like this collection of points very close to t0. So then what we want to do is I'm going to write down a bunch of symbols, and we'll make sense of them in a moment. We want to define, this is definition. We want to define instantaneous, let's say this is instantaneous velocity. So we're going to define instantaneous velocity at some time t0. And it's going to be defined as a limit. And I'll put this all in quotation marks because this is, I technically haven't made any of these ideas very precise, as h goes to 0. Because eventually the idea is like we want h to get smaller and smaller and smaller and smaller. So we're considering points in time closer and closer and closer to t0. And then what we want to do is take p of t0 plus h. So where's your position? What's the position at a point in time very close to t0 minus your actual position at t0 divided by the change in time, which would be t0 plus h minus t0, right? This is like your end time and this is your start time. And then so this simplifies. I don't know why is this not going down. What the heck? I don't know why this is not going down. It's like just stopped. Oh, maybe there's too much in this document. I didn't think that could ever happen. That's really annoying. All right, anyways, let me just carry it over like this. So we can, of course, simplify the denominator a little bit. So the t0s cancel and we get the limit, again, in quotation marks because I haven't made this idea of a limit precise, but hopefully it's like you have this rough intuitive idea of what it is. So it's the change in position over h, this number h, and you're going to take h as it goes to 0 because you want to take, basically you want to take average velocities on small intervals very close to t0, the time t0. And then you're going to take this limit as h goes to 0 because you want to take points in time closer and closer and closer to that desired point in time t0. And then so basically what you're doing is you take this quotient right here. You fix a t, compute this quotient. This gives you the average velocity. Take a smaller, even smaller t, compute this fraction again. This will give you a better approximation of the instantaneous velocity, this quotient right here. And then you just keep repeating this process. You'll get this sequence of numbers, and you get the instantaneous velocity at time t0 by taking this limit as h goes to 0. H won't actually equal 0. It will get very close to 0. All right, so let me open up. Oh, wait, now it's working, I guess. No, it's not. Oh, yeah, okay, so it's finally letting me scroll down a bit. So, so v of t, instantaneous velocity at time t0, is the limit as h goes to 0. Again, this is all in quotation marks because we're just trying to get a feel for what a limit should be. And then we'll actually state a definition, like a rigorous mathematical definition. So it's going to be, I'm sorry, let's try not to make mistakes as I write. But it's hard when you're talking and writing. So it's going to be this limit as of this quotient of p of t plus t0 plus h. So, and then minus p of t0. So your point at this time, maybe a little bit before or after t0. And then this is your position at actually at t0 divided by h. So this is going to be our limit right here. This is going to be our instantaneous velocity. All right, so now that's the rough idea basically behind calculus, trying to make sense of this. And we're kind of one step towards this. Now we just need, we have this, maybe this rough idea of what a limit is, but we just need to make this more precise. And that's what we're going to do in the next section, but or the next video, I should say. But before I do that, let's look at one more aspect of this graph.